Okay, welcome. And again, we're going to continue on here just to do a few more examples, maybe talk about a few more things in terms of organic chemistry, since I guess technically today was the organic chemistry lab, so I guess it will kind of go good together. So we're just going to kind of pick up where we were left off, and again, do a few more examples and give you a chance to do some examples of some basic naming of alkanes and how to draw some of them as well. All right, so we sort of were talking about again here how to go about naming these guys, and here again we want to look at our structure and we want to count the longest continuous carbon chain. So if we just go straight across, we got 1, 2, 3, 4, 5, 6, 7, and 8. If we go at the top here and come down 1, 2, 3, 4, 5, 6, 7, and 8. If we go 1, 2, 3, 4, 5, 6. If we start up here, we're over here 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7. So it looks like 8 is the longest one. And as I reminded you last time, you do want to sort of try all of your options, if you will, and you want to make sure that you try every sort of combination so you don't miss it. So if you do have one where it is just the straightest, it's sometimes again easier to just kind of put the box around the straightest one. So our straightest one here had lost track there, 8, I think, right? 3, 4, 5, 6, 7, 8. So the base of our name here again going to be octane based off of the 8 carbons that are present. Then we also do have some groups attached. So here we have a 1 carbon group, which is our methyl group. Here we have another 1 carbon group, which is our methyl group. And over here, we actually have a 2 carbon group. So our 2 carbon group would be based off of ethane, and it would become a ethyl group. So kind of putting some of this stuff together, we have definitely a dimethyl happening. For our 2 methyl groups, we have an ethyl happening. So again, it's important to number the longest chain. And again, in this case, we want to give our groups the smaller numbers. So if we go left to right, we got a 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, and 8 carbons. And if we went left to right here in blue, we would have groups at carbons number 2, 5, and 6. Now, if we number it the opposite way, going right to left here, we would have 1, 2, 3, 4, 5, 6, 7, and 8. And if we went kind of the green approach, we would end up with groups at 3, 4, and 7. So again, we want to go with the lower number, and it is as simple as 3 is more than 2. So we will go with the kind of blue numbering here, which gives our guys the smaller numbers. And in this particular case, that means that at carbon number 2 and carbon number 6, we have our dimethyl, right? So we'll do something like that. At carbon number 5, we have our ethyl. So now we want to put this in alphabetical order. And again, we're going to ignore the prefix. So we are looking at E versus M. And E would actually come first, again, even though it has the larger number here. So this would be 5 ethyl, 2, 3 dimethyl, and octane. That is quite a name right there, yeah. And a couple of things that we talked about earlier, we see that between a number and a letter, we have our dash. Also here as well, a letter and a number or dash. And again, between 2 numbers, we have our comma. and again our dash between our number and our letter. Any questions on that name? I hope they come up with the same name. That would be good. 5-ethyl 2,6. Oh, it is 6. I just did that. So let me fix mine then. Thank you. I just can't count apparently, right? There we go. They are right. I had it written right here, but not over here. So that is a 6 over there. Yeah, that's better. There you go. So again, that should be 6 as what we have right here. And again, that should be 6. Okay, now we're good. Yes, it would. Thank you. I think I was looking at the green 3 on the bottom there when I was doing it. It's good maybe to get rid of the second numbering when you just use it. So yeah, so it should be a 5-ethyl 2,6 dimethyl octane. And again, it was good. I did have the 6 here, I guess. That's good. I just forgot when I put it over there. All right. So why don't you take a couple of minutes here and try a few of these, do better than I just did there. And there's actually 3 guys here. So why don't you come up with the names for these 3 guys, and then we'll talk about it. So again, for those coming in, we're just working on the names of these 3. I drew the little line structures above it, just give you a comparison of what they look like. Okay, let's take a look and see. So starting here at the top one, I think 1, 2, 3, 4, 5, 6. We could also go 1, 2, 3, 4, 5, 6. You get 6 if you go up and up, and I think you get 6 if you go that way. So I think no matter which way you go there, it looks like 6 is going to be a winner. And that means that, again, it might just be easier to take just the straight 6 here. So obviously 6 in a row is going to be based off of hexane. We have a methyl group here, which is a 1 carbon group. Here we have a 2 carbon group. So that's going to be an ethyl group. And now we want a number. So if we go left to right, we got 1, 2, 3, 4, 5, and 6. I'm going to hopefully screw this up this time. We got 3 and 5 if we go in that direction. If we go the other direction, we have 1, 2, 3, 4, 5, and 6. And that means that carbon 2 and carbon 4 here. So in this particular case, we do want to go with the 2 and the 4 as it's smaller. So again, let's not mess this up this time here. The 2 goes with the methyl and the 4 goes with the ethyl. And we are going to put it in alphabetical order here. So putting that together going to give us 4 ethyl, 2 methyl, and then our hexane. Any questions on that name there? All right, so looking at the guy on the left here, we got 1, 2, 3, 4, 5, 6, 7 carbons going that way. 4 carbons if you start on top and go to the right, and 1, 2, 3, 4, 5, 6 carbons if you go the other way. So our 7 carbons zigzagging over this way. That leaves us 7 carbons, which is heptane. We have our methyl group here, and again, if we look at our line structure, and then this would be our methyl group, right? And we do want to give some numbering here. So if we go kind of left to right, we're going to end up at 1, 2, 3, 4, 5 for that group. If we go right to left, we will have 1, 2, 3 for that group. So obviously going in this direction here, we'll give our methyl group the smaller number, which would be 3 methyl. And that's pretty much what we need to put together. That gets us 3 methyl and then heptane. Any questions on that one? Now looking at the one on the right, again, we're going to be looking for our longest carbon chain. So that's going to be 1, 2, 3, 4, 5, 6. Looks pretty good. We got 1, 2, 3, 4, 5, 6, 7. So that's even more. We got 1, 2, 3, 4, 5, 6, 7, and 8. That's even more. So in this case, again, the longest continuous chain, I don't draw lines all over everything, is actually going to be 8 in this case. So again, you do want to check all your options there, so you don't miss anything. And let's just kind of put a box over that. So we do get 8 heading down, around, and sort of back up, if you will. So that is 8 carbons, which is octane. And at this point, what we got is we do have over here a 1 carbon group, which is our methyl group, right? Over here, we have a 2 carbon group, which is our ethyl group. So now we just need to number the chain and sort of figure out which way we want to go with it. So if we go this way here, that would be 1, that would be 2, this would be 3, this would be 4, this would be 5, 6, 7, and 8. So going sort of in the green direction, we have a group at carbon number 3 and a group at carbon number 5. If we number in the opposite direction, 1, 2, 3, 4, 5, 6, 7, and 8. We have a group at carbon number 4, it looks like, and carbon number 6. So again, it does look like the green way is going to give us the lower number, which is what we're looking for. So that means that my methyl group going the green way is carbon number 3. And my ethyl group here is carbon number 5. Again, we're going to go alphabetical. So E is going to come before M, even though number-wise, they're sort of opposite. So putting that together gets us 5 ethyl, again, dash between number and letter, 3 methyl, and that was octane. Any question on those names there? So why don't you do these two here and see what you come up with. Actually, you know what? Let's not do those. I think they almost look the same, if I'm not mistaken. Those do look the same. I think those are the same. They just came back. Okay. Let's not do those. Let's go to these then. What's the idea? Like, wait, those look very familiar. Let's actually talk about then here. This would be good too. Why don't you give these a try? Why don't you try to actually draw the structures here? So why don't you draw the structures? Why don't you draw both the condensed formula and why don't you draw the line structure for each of these and see what you come up with. So why don't you give this a go, which I think should be different. So this, you actually have the name, but you want to draw the formula. So work your way backwards. And I'll give you a hint. That is sort of how you approach it, work backwards in terms of the name. So why don't you take a couple minutes and actually try to draw these guys here. Okay, so let's take a look. And I actually think that when you're given the name, it's actually the easier of the two than necessarily maybe kind of naming something. Because when you're given the name, you essentially have everything that you need to draw it. And a really good approach when you're given the name and you want to draw it is to kind of always work backwards. And if you work backwards, it gives you some information. So butane automatically tells you it is 4 carbons. And that's really what you should start with. It's just sort of the carbon backbone, if you will. Nothing else attached, just kind of attach them all. I'm going to leave a little bit of room because we're going to add some stuff. And then what we have is dimethyl. And again, the methyl is the CH3. And the di would mean that we have 2 of them. Excuse me. And they are at locations 2 and 3. And the nice thing about you drawing it is you could decide whichever way you want to go. You could go left to right and go 1 through 4. You could also start right to left and go 1 through 4 because you're drawing it again. You could go either way. I personally am going to go left to right. So I'm going to call this carbon number 1, which means as I go to the right, that's going to be carbon number 2, carbon number 3, and carbon number 4. So I would go to carbon number 2 and I would put my methyl group. I would then go to carbon number 3, which would be right next door, and put my methyl group as well. And that again basically takes care of pretty much everything we got in terms of that name. So what is left at this point is to make sure carbon's got 4 bonds. And to do that, we're just going to use hydrogens. So the guy at the end has 1 coming in, so he needs 3 hydrogens. The guy next door has 3 coming in, just needs 1 hydrogen. Guy also here needs just 1 hydrogen to get the 4. And we would need 3 hydrogens there to get the 4 at the end. And again, this would be the condensed formula as we don't draw it out. If we did our line structure there, that would be something that looks like that. That's 1, 2, 3, 4 carbons. At carbon number 2, we have a methyl, so we just draw a line. And at carbon number 3, we have a methyl as well, so we just draw a line like that. Any question on that particular one there? We're going to take the same approach here for the next guy. We're going to, again, work our way backwards. So starting here at heptane, that's going to be 7 carbons. All right, so 1, 2, 3, 4, 5, 6, and 7. That takes care of that. At carbon number 3, we have an ethyl group, which is a 2-carbon group. So again, you could decide left to right is 1 or right to left is 1. So I'm going to go left to right. So I'm going to call this carbon number 1 on this end. So if this is carbon 1 here, we go to 2, we go to 3. I'm going to put my ethyl group, which again is that 2-carbon group, looks something like this. You could write it on top. You could write it on the bottom. It doesn't matter. They're both the same. So that will take care of that. My methyl group, which is the 1 carbon, carbon number 2. So since I decided on the left is number 1, this would be number 2, and we would put our methyl group there. And again, at this point, everything else is going to be hydrogens. So the guy at the end needs 3. Guy next to it needs 1. Next to it needs 1. We need 2 there, 2 there, 2 there, and 3 at the end. And again, we do our line structure, looks something like this. 1, 2, 3, 4, 5, 6, 7, I believe. 1, 2, 3, 4, 5, 6, 7. And again, at carbon number 2, we have our methyl group. And at carbon number 3, we have our ethyl group, right? Looks something like that. Any questions on those two? So now, let's see here. Working backwards on our last one, which is pentane. So that's going to give us 5 carbons there. Takes care of that. Again, I'm going left to right. So my number 1 carbon is going to be on the left. So at number 4, I need to put a methyl group. So 1, 2, 3, 4 will give me a methyl. And then at carbon number 2, I'll have a chloral. So remember, chloral is how we name chlorine, right? So that is number 2. And that means that we're going to need 3 hydrogens there. This guy will only need 1 hydrogen. He'll need 2 hydrogens, 1 hydrogen, and 3 hydrogens at the end. Again, our base is 5 carbons, which looks like this. And again, here at carbon number 2, we have a Cl, and carbon number 4, we have a CH3 that looks like that. Any questions on how to draw them from the name? Both line structure or condensed structure. Again, I do think this is probably the easier of the two, going this way. Any questions on those there? All right, so just to make sure, we'll come back this way. We won't do these two because they look the same, but we draw you a couple here in line structure and you can name them. So let's see, we'll do all right, so why don't you give the name for this one? And why don't you do oops, come here. And do that. And do that. All right. Why don't you take a minute or two here and come up with the names for those two structures? Semi-good drawn. Okay, let's take a look here. So we'll start on the one on the left. So we want the longest carbon chain. So again, that's a carbon 1, 2, 3, 4, and 5 if you go down. 1, 2, 1, 2, 3, 4, 5, 6 if you actually go up. And we do see actually 6 here is the longest continuous carbon chain. So actually, even though it may appear the other way, it's actually this guy right here. So 6 would be, what we got there? Hexane. Now, in terms of the groups, we have a Br, which is a bromol group. And again, a line with nothing at the end of it is a methyl group. So we do want to number it, whichever way will give us the smaller set of numbers. So looks like if we go 1, 2, 3, 4, 5, and 6, we will have stuff at carbons 2 and 4. If we go the other way, we will have 1, 2, 3, that group, 4 and 5 for the bromine. So it looks like it is 3 and 5 if we go the other way. Again, a little bit larger in terms of the numbers, so we want to go with the smaller. So we will go the way I numbered it there. And alphabetical, it is going to be the bromine first. So we should have something like 2 bromol. Maybe I can squeeze it in. 4, probably not, methyl, and then hexane. So I'll just kind of carrot it up there. So 2 bromol, 4 methyl hexane. Again, the methyl hexane part, all kind of one word, would be what you'd get there. So here, I'll just write it here down this way then. Hexane. Cross that out. So 2 bromol, 4 methyl hexane. So again, sometimes in line structure as well, it's kind of deceiving because you sometimes will just focus on kind of the one straight in front of you. You do want to make sure you kind of go through and make sure you catch, how many carbons there may be. So if we go to the guy on the right, same deal. We'll start here, maybe where you might think 1, 2, 3, 4, and 5 if you go that way. 1, 2, 3. If you went down right there in the middle, that would be 4. Started over here on the left. 1, 2, 3, 4, 5, 6, and 7. If you go up, now you do have another option. This would be starting here. 1, 2, 3, 4, 5, 6, and 7 as well. So it looks like, if I'm not mistaken, 7 looks like a winner. 1, 2, 3, 4, 5, 6, 7. So however you want to get that 7, again, you could go, this way is for 7 as well, which comes across like so. I feel like this guy's missing a circle, so I'm just going to put it there for fun. All right, so in the box or the circle there is 1, 2, 3, 4, 5, 6, 7. That's going to be heptane. And now what we got is that's a methyl, that's a methyl, and that's a methyl. That is 3 methyls in this compound, so that is a trimethyl situation happening. So we do need some numberage. And again here, in terms of the number, let's go this way. We'll go kind of left to right. That's going to be 1. That's going to be 2. That's going to be 3. That'll be 4. That'll be 5, 6, and 7. So going that way, it looks like we have 2, 3, and 4. If we went the other way around, starting where the 7 is and calling that number 1, that would be 1, 2, 3, 4, 5, 6. So we would have 4, 5, which is obviously a much larger number. Now, a couple of things. We do need to give a location of each of those. So we are going to use all 3 of those numbers. So that's going to give us something like 2, 3, 4 trimethyl and heptane on the one I just made up. There we go. Any questions on that name or both of those names there? I guess would be this guy over here. Or any questions on naming or drawing in general? Okay. We'll skip some of that. So let's just talk a little bit about cycloalkanes and how to name those guys as well. So as I mentioned before, cycloalkanes for sure, usually in most cases, people use the line formula, and these are sometimes referred to as sort of like the geometrical shapes that you see. So we got our triangle, we got our square there. And as we talked about, because it's sort of a ring structure, they do lose a couple of hydrogens to close that ring. So we do get CN H2 times N as sort of the general formula here. So again, this has essentially down here 1 carbon, 2 carbons, and 3 carbons. Again, 3 carbons is based off of propane. But because it is this sort of ring structure, we do put the cyclo in front of it, and that's how we get to cyclopropane. And again, it's missing the 2 hydrogens that propane would have when it's a straight chain alkane, which would have this formula here. So it would be C3H8, as opposed to here, we're in the cycloalkane, C3H6. Again, the 2 missing hydrogens allow these guys to come together basically and kind of close the ring. And just like normal, it has 2 lines coming in. So technically speaking, although never really drawn, the hydrogens are 2 on each of those guys. But again, usually just seen as more of a geometrical shape, if you will. This has over here 1, 2, 3, and 4 carbons. And 4 carbons is based off of butane. Again, because it's a ring structure, cyclobutane is what we would call that guy there. There's our cyclopentane, which has our 5 carbons on it, and our cyclohexane, which has our 6 carbons on it. So how do we name these guys? Again, we do put the cyclo in front of it. If it is sort of mono-substituted, if you will. So for example, if you have mono-substituted means it just has one sort of group attached. Yeah, something like this. This would be methyl cyclopropane. Again, the big group here, longest carbon chain, would be the cyclopropane part. And here with nothing attached, that would be the methyl group. Nothing written at the end of the line, I mean, and a methyl cyclopropane. In the case where you have just one group attached to a cycloalkane, which is what these guys are, you don't have to give the number or the location of anything. It's assumed that wherever that is drawn is going to be carbon number 1. So technically speaking, if you drew it like this, or you drew it like this, they're all the same. They're all methyl cyclopropane. Again, because it's the only group attached in this ring structure, if you were to number, this technically would be carbon 1 here. This technically then would be carbon 1 here. And this technically would be carbon 1 here. And again, you don't need the number here because technically wherever that ends up, because it's the only group there, would be carbon number 1. If you do have, though, multiple groups attached to a cycloalkane, then you do need to number the ring. And you do need to number the ring just like we numbered the alkanes. And we want to go for the lowest numbers. So here, when we look at this guy, the biggest carbon chain, if you will, is the cycloalkane. Yeah. And again, if we look at it, 1, 2, 3, 4, 5, and 6, which is where the base of the name comes from here as cyclohexane. We also have 2 groups attached. We have our methyl group here. We also have our ethyl group. So we do want to do some numbering. So one option would be go this way. 1, 2, 3, 4, 5, and 6, right? Now you could go the other way. 1, 2, 3, 4, 5, and 6. So if we go clockwise, we have groups at 1 and 3. If we go counterclockwise, we have groups at 1 and 5. And obviously 1 and 5 is a larger number than 1 and 3. So we wouldn't want to go that way. But now there's also another consideration to think about when you're naming alkanes here is the idea that the importance in terms of alkanes, in terms of the groups that are attached, are alphabetical, which means when we go to name this guy, we are going to go with the E before the M. So in my first set of numbering, I actually started with the methyl, which is the M, which is not really alphabetically how we might go. And we are going to go with the ethyl first. So what that means is you may want to, usually in this case, start with the alphabetical guy first in terms of numbering. And that would mean that if we went alphabetical starting with our E, we would start with a 1 here. We also have two ways we could go. We could go 2 and 3, which gives us a group at 1 and 3, just like we got with this guy, right? When we started with the methyl. We could also go 1, 2, 3, 4, 5, which is also what we got when we started with the methyl, right? Which is what we scratched out here. And just like we did over there, we would scratch it out. Now, it's kind of a tie no matter which way you go, right? So if you start with the methyl and go one way, you get 1, 3. If you start with the ethyl and go one way, you get the 1, 3. So since it's sort of a tie in terms of the numbers, the next important thing is obviously the alphabetical aspect of the groups. So we would want to give the ethyl the smaller number in this case because it is alphabetically going to go first. And again, this is because it doesn't make a difference in terms of the number which way you go, in terms of if you start with the methyl numbering or you start with the ethyl. So then we sort of want to default back to the next important thing, which would be the alphabetical. So we would go with 1, 3, but we would go with the 1, 3 starting with the ethyl. And our methyl here would then be our 3, again, because alphabetically ethyl is going to come first and there is no difference whichever way you go. So putting all that together, we do get 1 ethyl, 3 methyl, and cyclohexane. That is a mouthful right there. Any questions on that? So sometimes when you're numbering, this does happen. Sometimes when you're numbering, if you go left to right or you go right to left, you end up with kind of the same numbers for the groups. So what is the sort of the next important thing in determining which way you should number is going in that alphabetical order with alkanes here. So again, in this case, like we just saw, if you started with the methyl and went around, you got 1, 3. If you started with the ethyl and went around, you got 1, 3. They're both the lowest set of numbers, so then you want to default alphabetically. Ethyl should come first. Other questions on that? So here, as I mentioned before, if it's just mono-substituted, which is what both of these are here, again, mono-substituted just means that there's one substituent, some type of group on there. We just use the group name. We don't have to give the number. So on the left here, we would have methyl cyclohexane. Again, a 6-member ring there, which is our cyclohexane part, and the methyl group. And again, the number is not necessary because it's the only thing there. And if you did need to number, it is assumed that this is carbon number 1, where that group is at. Same thing over there on the right. We got 1, 2, 3, 4 carbons in a group that's attached based off of butane. And that is how it becomes a butyl group. And then our ring structure is a 5-member ring, which gives you your cyclopentane. And obviously, as we just talked about there, we do want to go with the lower number alphabetically, again, if it does not make a difference in terms of which way that you number. So as you can see here, this is a little bit different. This is 1,3-dimethyl cyclohexane. In this case, it doesn't matter whichever way you go because they're both methyls. So the 2 methyls there is where the dimethyl comes from. Again, carbon 1 and 3 is where the numbers come from. And then our 6-member ring here, which is our cyclohexane. And then this, I think, is the one we just did. They just kind of turned it around, as you can see. A little different orientation, 1-ethyl, 3-methyl cyclohexane, which, if I'm not mistaken, should be that one we just previously did. Right here, right? 1-ethyl, 3-methyl cyclohexane. Here you can see the way it's drawn here, you get that name. And even if you sort of drew it the other way, like they did in this one, you still end up with the same. Again, you would start here, and it's the same structure as well. All right. So a lot of organic guys are used as natural gas, petroleum, like gasoline. It's just a long chain of carbons. How they sort of break those up is what is sometimes referred to as fraction or fractioning. And basically, they just take really long chains of carbons and hydrogens together, and they break it down into smaller ones. Hence, like regular gasoline, right? Octane, right? So much octane, that's basically 8 carbons, right? So they break it down into that, and we use it as sort of fuel. As we talked about a little bit before in terms of some of the properties here, because really alkanes are nonpolar, they're basically made up of those carbon-carbon bonds, which is a nonpolar bond, the carbon-hydrogen bond, which is nonpolar. Again, they're going to be using those dispersion forces, and those are the weakest, as we talked about earlier today, of those intermolecular forces. So the weaker the intermolecular force, the lower the melting point and boiling points that you'll have for these organic guys. And as we talked about a little bit earlier as well, you know, when you get some different functional groups in there, perhaps an OH group and an alcohol, that significantly raises the boiling points and melting points of those guys compared to something like an alkane. Again, because it has the ability to do some hydrogen bonding that these guys cannot do. So remember, those dispersion forces are those weak forces, and they have very low melting points and boiling points. And that's why a lot of smaller alkanes are gases at room temperature. Again, because they have those very, very weak forces. One thing about dispersion forces, as you may also remember, the strength of the dispersion force actually increases with increasing molecular mass, right? The more molar mass there is, the longer the sort of compound there is, there's more electrons, there's a greater chance of polarizability, right? The electrons moving to one side or the other and creating stronger dispersion forces, right? So that's why the smaller alkanes that don't have as many electrons have very, very low intermolecular forces in terms of strength. And that's why they're kind of gases, right? Things with very low intermolecular forces, or I guess low is the wrong word, kind of weaker intermolecular forces is probably the better word there. Usually will be more in the gas state. It's easier for them to get apart and go into the gas state. Alkanes, like I said, since they are pretty much nonpolar, are going to be insoluble in water. Remember, that also just goes back to the idea of like dissolves like. Right? And so polar and polar things are good, right? Non-polar and non-polar guys are also good. But when you try to mix that polar and non-polar together, not so good, right? And that's basically what happens when we do mix an alkane, which is nonpolar, with water, which is polar. You typically will also get sort of different layers. So if you have a test tube that has something that's organic in it and something that's aqueous or water-based, usually the top layer is your organic layer. Usually the bottom layer there is your aqueous layer. And also what happens with oil spills, for example, right? In an oil spill, the oil just kind of floats on the ocean, right? When those tankers kind of spill and stuff like that. This is also what we're looking at here in terms of boiling points. These are all alkanes. The difference really between all these is like the molar mass, right? It's increasing as you go this way. And what we see in terms of the boiling point is it's also increasing as you go that way. Again, that's back to what I was just talking about. All these guys are going to use dispersion forces as their main source of interaction. And because there is more atoms and more electrons than the guy on the right, there's a greater chance of those temporary. I just want to hang on once here. Okay. Let's see, remember, you can still hear me. Yeah, just kind of, I think it's froze there for a second. I hope. Okay, so I think hopefully everybody can hear. Not sure. All right, let's get everybody back in here. All right. All right. Hopefully everybody can hear me now. It's just in case it looked like it kind of froze there for a second. But just to recoup, just in case, so I apologize if you could hear me or not. But again, a common reaction that occurs with our alkanes is a combustion reaction. And a traditional sort of organic combustion reaction usually has oxygen on the reactant side. And on our product sides, we usually do produce CO2 and water. Now, just a generic combustion reaction is basically just the presence of O2 is pretty much all you need, and you would have your combustion reaction occurring. But this is usually what people think about in terms of combustion is an organic plus oxygen. Usually will involve energy, flame, right? That's what happens when we light a Bunsen burner. But sometimes you do get a incomplete combustion reaction. Really, the only difference between a combustion reaction and an incomplete combustion reaction is that instead of CO2 on the product side, you get some carbon monoxide that gets produced. And again, most of the time it is a complete combustion and you get that CO2 produced. Another sort of important type of reaction that alkanes undergo is a type of reaction which is known as a substitution reaction. So, in chemistry or organic chemistry, there's kind of like three types of reactions. There's a substitution reaction, there's an elimination reaction, and usually there's an addition reaction. And a substitution reaction is what alkanes basically will undergo. And it is what it sort of sounds like. Basically, a hydrogen on an alkane gets substituted out. And you basically remove a hydrogen and you replace it with a halogen, which is why it's called a halogenation action. So, for example, if we take this guy and we react it with Br2, which looks something like this, right? Let's put Br2 like that. So, in this case, when you look at all these hydrogens, pretty much they are all equivalent to each other, which means they're all exactly the same. And usually, when you do this reaction, you'll sometimes be asked to just do what is sometimes referred to as the monosubstituted product, which basically means just take one of the hydrogens. So basically, you could choose any hydrogen you want. I'm going to choose this one. And basically, what's going to happen is this guy's going to come off, and substitution in its place is this bromine. It's going to come on in its place. So the nice thing about organic reactions for the most part is, well, the non-nice thing is a lot of people make it a lot harder than it really is. And there are certain things that are a little bit more difficult, but for the most part, in an organic compound, when it goes through a reaction, there's really only kind of one spot that sort of changes in a lot of reactions, a lot of the basic reactions. And that means you could essentially just draw it exactly the way it was before. And the only difference is we're not going to draw the H that came off, but in its place, we're just going to draw the Br that came on. And when you kind of keep track of everything, we have an H plus that came off. When this Br breaks apart, it becomes Br minus. So these two guys will actually come together as well, and we will get HBr this form. Yeah? So here we will get our alkane, right? And this is what is sometimes referred to as a haloalkane, like it is here. Halo because it has now a halogen that's attached, and a hydrogen halide, which is what this is referred to. And it's pretty much what the name sounds like. Hydrogen because there's hydrogen, halide because it is basically a halogen with a negative charge. So in a monosubstitution product, you just replace one of the hydrogens. If you let it go, you technically could replace all of the hydrogens in theory, but usually just replace one. So same thing here, even though it's a ring structure, there's all these hydrogens at each of those spots. So basically one will come off. And again, one of these guys will come on in its place. Usually you need heat or light to do that. And everything's the same. The ring doesn't open or anything weird like that. You just put a bromine on there and you get bromol cyclohexane at the end there. So again, this is what is referred to sometimes as a substitution reaction. When you take organic chemistry, you'll get into the nuts and bolts of how that actually happens in terms of bonds breaking, electrons moving, drawing arrows where all the electrons go. So a lot of organic chemistry is mechanisms of how these reactions occur. So this is kind of the overall reaction, but you will, in real organic chemistry, unlike this fake one we're doing right now, you will learn all about sort of the electrons and electron arrows that push electrons and bonds breaking and making and all those kind of things. Any questions on alkanes there? All right, so just take a couple of minutes here and just talk a little bit about alkenes and alkynes. I think was in that chapter as well. But just so if anybody's listening, up until what we just talked about is sort of fair game for the final. This is just, some knowledge information. So this stuff here will not be on the final. Final information back, yeah. So final stuff back, this stuff again, just to kind of finish it up a little bit in terms of some of these topics. All right, so talking about these guys here, alkenes and alkynes. Alkenes, again, the functional group is the carbon-carbon double bond is the functional group. Triple bond here for our alkynes. And a couple things happen as we go from an alkane to an alkyne and an alkene. And an alkane, if you remember, looks something like this. And again, here we have that tetrahedral geometry. And by the way, the hybridization here would be sp3. Yeah. To remind you how you do that, right, is basically count up electron pairs. So there's 4 electron pairs, sp3. We do get a change in both geometry and hybridization here when we add that double bond. This now has 1, 2, 3 electron pairs. Also has 3 bonds. And that is what is known as trigonal planar, right? And that is where the 120 degree comes from. By the way, the hybridization of this guy, 3 electron pairs, would be sp2 hybridization. So again, the hybridization here on this guy is sp2, also gets your 120 in terms of that double bond. They also have that formula just like cycloalkanes of C and H2N times or H2N. Again, they lose those two hydrogens like we talked about earlier by making the double bond. Alkynes, on the other hand, also has some different geometry. Again, if we look at the geometry here for this carbon and even the carbon on the right, that is 2 electron pairs. Remember, double bonds and triple bonds count on as 1 electron pair and 2 bonds, and that is linear in terms of geometry. So 180 degrees. Also has that extra 2 hydrogens lost as we make that third bond that's happening. And in terms of hybridization, 2 electron pairs, we are looking at sp in terms of the hybridization. Important when you get to organic, knowing those things. So in terms of sort of physical properties, they do share very similar physical properties to alkanes. They are still nonpolar, so they still have low melting points and boiling points. They're also going to still be insoluble in water, but they are, as we talked about earlier as well, now what are classified as unsaturated hydrocarbons. And they're unsaturated again because of that double bond or that triple bond. Those carbons now lack the maximum number of hydrogens that are possible. So again, we do call them unsaturated, and same thing with our triple bond. Again, from our carbon-carbon single bond, obviously down a number of hydrogens here, and these are both considered unsaturated because of that. And we do show the double bonds here, both in condensed formula and also even line formula, right? So if you had something like this, you would draw it something like that. That's not reflective of what's down here. What we got going on down there would look something like this, I think, which would be this guy here. And even the triple bond there, you know, you would show it the same way. So you can incorporate obviously double bonds, triple bonds in there. You know, if it's a double bond that is like with an oxygen, again, you would show it like that as well. You know, that's obviously has an oxygen attached to it, but you know, we incorporate these sort of double bonds into there. Now, for alkenes and alkynes, the way that we name them is simply we take that alkane name, which ends in ane, and we drop it. So if we have our double bond, it becomes ene at the end. If you have a triple bond, it will become yne at the end. Now, there is sort of a different rule when we're naming these guys. And when we get to a situation where probably about 4 or more carbons, where there is a option as to where the double bond may be or the triple bond may be, we do need to give the location of the double bond or the triple bond. Here, for example, this is just going to be 3 carbons, by the way, even though it's drawn this way, 2 and 3. And that's going to be based off of propane, and this will be propene. You don't technically have to call it 1 propene, because if we went this way, this would be 1. If we put the double bond over here, it would also be number 1. So it's kind of the same no matter where it would be put. But when you do have that option, you do have to kind of put the number of where you put the double bond or triple bond. Now, in terms of priority, when you get to an alkene or an alkyne, the double bond or the triple bond gets the priority in terms of numbering. So you want to number whichever way will give the double bond or the triple bond the smaller number when you need to do that. So that's a very important sort of distinction. So when we look at this, again, you're still going to be looking for the longest continuous carbon chain. So you got 1, 2, 3, 4. By the way, the longest carbon chain does need to contain the double bond or the triple bond. If you went the other way, 1, 2, 3, 4, What you can't do is go 1, 2, 3, and not include the double bond. So again, no matter which way we go here in terms of the double bond, we are going to get 4 as our longest continuous carbon chain that again contains that double bond. So 4 carbons is based off of butane. It has a double bond, so butane becomes butene, E-N-E, just like alkene. And now we need a number, right? So if we go this way, by the way, we still have a group that's attached, which is a methyl group. And now if we go to number, we could go 1, 2, 3, 4. Or if we go the other way, we could go 1, 2, 3, 4. Now, this is what I'm talking about previously. Before we did it with alkanes, we would go right to left because that would give the methyl group the smaller number. But because this has a double bond, or if it had a triple bond, we want to give the priority to the double bond or the triple bond. And that means that we actually want to number in the purple direction here, because in the purple direction, it's going to give our double bond the smaller number. If we went right to left, it would give our double bond a number 3. If we go left to right, it gives our double bond 1. So we would want to go that way, which means this is 1 butene, the 1 for the location of the double bond. And because we locked into numbering in this direction, that means that we have to number our methyl group with the same numbering. And that means that our methyl group will end up at carbon number 3. So this would be 3 methyl, 1 butene. Any questions on that one? Same thing with our triple bond here. We'll do the same approach. If we go 1, 2, 3, 4, 5, 6, we go 1, 2, 3, 4, go up, 5 and 6. Looks like 6 no matter which way you go, so might as well again take the straightest way. So 6 carbons is going to be based off of hexane. It has a triple bond in this case, so the ANE is going to become, right, hexine, YNE. Again, we want a number, whichever way is going to give not the group in this case, the smaller number, but our triple bond. So our group, by the way, is an ethyl group here. And going right to left looks like it will do that. We'll go 1, 2, 3, 4, 5, and 6. Again, going right to left gives our triple bond the number 2. If we went left to right, our triple bond would end up at carbon 1, 2, 3, and 4. So again, going the opposite way gives us a smaller number. So that is 2 hexine. Again, the 2 is the location of the triple bond. And because we're locked into now numbering in this direction, we have to number our ethyl group that way, and that would be 4 ethyl, 2 hexine. Any questions on those 2 names? So that hopefully should say what we just did, if I did all my counting right, hopefully. All right, 4 ethyl, 2 hexine, looks good. So why don't you take a couple minutes here, why don't you try these 4 and see what you come up with the name, and then we'll talk about it. Okay, so let's take a look and see how we're doing here. So we have 1, 2, 3, 4 carbons in a row. We do have a double bond. So again, 4 carbons going to be based off of butane. Because we have that double bond, it now becomes butene. We do want to give the double bonds location here. And again, 1, 2, 3, and 4. And again, that will give that guy the smaller number. If we went the opposite way, our double bond would end up at carbon number 3. Looking at our next one here, still same deal. 1, 2, 3, 4, which is also butene. But again, why it's important to give that double bond location. I'm sorry, that first one should be 1. My bad. I'll learn to count one of these days. There we go. That should be 1 butene. It is right here at carbon number 1. There you go. All right, so that's 1 butene. Here's 2 butene right here. Again, the double bond is at carbon number 2. So again, why it's important to give that is so that you get the correct numbering. And again, hopefully you could count better than I did there. Coming this way, we do have 1, 2, 3, 4 carbons, and also have 4 if you went 1, 2, 3, 4. So again, if we just kind of take the straight guy here, that also is going to be our butene. Also going to be, if we went left to right, 1, 2, 3, 4. If we went right to left, 1, 2, 3, 4. Now, in terms of the double bond, as we can see here, if I went left to right, double bonds at carbon number 2. If I went right to left, double bonds at carbon number 2. It is a tie in terms of which way you go for the double bond. So this is where we then want to kind of go to the next most important thing, which would be our group in this case. And there is a difference in terms of ring for the group. If I went 1 left to right, we would be at carbon number 3. If I went right to left, we would be at carbon number 2. So I would want to go our right to left because that's going to give the methyl group a smaller number. So putting that together would give us 2-methyl 2-butene. Any questions on that one there? And our last one is just 4 carbons straight in a row. But here we do have a triple bond. So we're going to come butyne, and location does not matter which way you go. 1, 2 if you go that way, 1, 2 if you go that way. So that would be 2-butyne. Any questions on those there? Okay. All right, let's get that. So why don't you do these two here, see what you come up with. Hello. Hello. All right. Hopefully it comes back. I think we're back. Hopefully. Yes. Okay. Okay. Perfect. Okay. I just want to make sure. All right. So I saw this like way delay happening, like on my side. I'm like, it doesn't look like it's speaking. So just want to make sure. I think we're back. I hope. All right. So let's go back here. All right. Okay. So just to make sure, again, I hope everybody, and I apologize if you did hear me or not. But again, these are the two names, and just quickly, just to refresh, just to make sure, just in case there was no audio at that point. Um, we got 7 carbons in a row with a double bond, which is where the heptene comes from. The 3 is where the double bond is located. And then obviously, because we had to go numbering that way for our double bond, the ethyl group gets a number of 3 because of that, and our methyl group gets a number of 6. Again, E before M in terms of the groups that are attached. On the bottom here, we had a run of 6 carbons in a row with a triple bond, and that's why we got the hexyne. The 3 you got no matter which way you went in terms of the numbering. So in this case, like we were talking about previously, regardless of the way we went, the triple bond was always the same number. Then we wanted to default then to the group that's attached and give it a smaller number. And that's why we ended up numbering left to right, because that gave us our bromine with a smaller number. All right. So like I think I was saying here is the last thing we're going to talk about here for the semester, yay, obviously, is isomers that basically develop because of these double bonds. And there's a certain type of isomer which is known as cis or trans isomers. And we talked a little bit about it, I think, when we were talking about complex ions. And cis basically means the same side, and trans means basically the opposite side. And what we're talking about here is the double bond. And in this case, we have a CH3 here and a CH3 here. Those are 2 groups that are on the same side of the double bond, and that would make it the cis isomer. While on this guy, the 2 groups are on opposite sides of the double bond, and that would make it the trans isomer. We don't get these type of isomers in alkanes because alkanes with a single bond, they are free basically to, with that single bond, rotate around that bond. They're freely able to rotate basically around it. We do get these cis and trans isomers with our double bonds because as that double bond occurs, these 2 guys come closer together and they sort of lock into place. And when they lock into place, you lose that ability to rotate about the double bond because of that, because of its trigonal planar geometry and those double bonds and even the triple bonds. It really loses those rotations. So again, here's just some different conformations. Even for the same guy, you have the same name, and sometimes they will put trans in front or cis in front of the name to indicate basically the locations of those groups. So there are 2 things that has to occur for you to have the possibility of a cis or trans isomer. Basically, what you need is on 1 carbon in the double bond, you need 2 groups that are attached that are different. So on this carbon on the left here, you need to have 2 things that are different attached. And then on the other carbon, you need to have a group that's the same as the previous carbon. So in order for cis or trans isomers to occur, when you look at the carbons in the double bond, the 2 groups are attached. And in the case of this, hydrogen can be considered a group. You do need 2 things that are different on the carbon. Same thing over here. You need 2 things that are different. But you also need some type of groups that are the same on both carbons. And we can see if we look at the hydrogens, they're opposites of each other, trans. If we look at the bromines, they're opposites of each other, is trans, and so forth. So if we look at this, when we look at this carbon-carbon double bond, we have a hydrogen and a hydrogen. That are two groups that are the same. And that automatically eliminates the possibility of cis or trans. Because again, you do need to have two different groups on that carbon. Now, stereoisomers are isomers that differ only in the three-dimensional arrangement, while constitutional isomers, like we talked about, again, differ in the way they're bonded to each other. So these are some constitutional isomers here. These are stereoisomers. These two guys, they're basically difference in their 3D arrangement. Here, these guys are on the same side, double bond, opposite sides of the double bond. But again, constitutional isomers with the original compound over here. So let's take a look at these and determine whether or not each of these can be cis or trans isomers. So let's take a look here. So when you're trying to determine that, what you want to do is look at the double bond. So the first thing you want to make sure is this guy here and this guy here, they are different, which is good. We then want to look over here, this entire group here and this entire group here are also different, which is good. And now the second thing that we really need is a group that's the same on the both carbons. So this group here, which is the CH3, is the same CH3 that we see over here. And that is the same group on different carbons, and they are opposite of the double bond. So the first guy here would be trans. Coming over here, if we look at the carbon-carbon double bond, this group and this group are different, which is good. But when we look over here and we look over here, these two groups are the same, which means that automatically eliminates the possibility of cis or trans. So none here, basically. And lastly, if we look over here, we have this group and this group, which are different. So that's good. We also have this group and this group, which are different. So that's good. And we also do see that between the two carbons, we do have two groups that are the same. And this group here and this group here are the same. And they're on the same side of the double bond, which means that this is going to be cis in this case. Any questions on that? Okay, I think we'll finish up here just talking about this one. When we look at this first one here, we have different group and different groups, which is good. The groups that are the same on opposite sides here of opposite carbons are the same side of the carbon, so this would be cis. This here, different groups, same group, but opposite sides, so this would be trans. And lastly here, different group here, different group here. Chlorine and chlorine is the same, so this would be neither in this particular case. All right, I think that's enough torture here for today and the semester apparently as well. All right, we'll stop there. That's good, I think. I feel like we got into organic at least a little bit. All right, so that now officially wraps up your Chem 51 experience here today and for the semester. So again, I'd like to thank you for showing up and listening. And again, like I said before, I did enjoy having you all in person when I was able to see you in person and online as well. And congratulations on finishing. Remember, again, we have our two finals next week, Tuesday and Thursday. So Tuesday at 10:30 for our lab final. Again, going to be more lab oriented. So you want to think about the experiments we performed. You want to think about the calculations type of things. And then obviously on Thursday, we'll have our lecture final, which will again cover all the chapters. including the organic up through the alkanes that we talked about and naming and stuff like that. And you do need to know the functional groups. And again, in terms of the homework, like we talked about in lecture, you don't need to officially turn in these last two chapters, 20 and 21. I would highly recommend, though, that you do those problems because they will be on the final. So if you take the final, you'll get credit for those two homework assignments, but you don't have to upload them or anything like that. Let's see. Other than that, any other questions on anything like that? Yeah, so the only one if you still have out, you should upload chapter 19. So let me think what we can do with that. I believe the upload for exam 3 is still up there. So I think you should still also be able to upload chapter 19. So I'll put out an announcement to do so, but if you want, you could just go back through there and upload just the chapter 19 part of it, and then I'll go give you credit for it and stuff like that. Okay, so I think it's still, even though if it says late, it should still be open for you to upload it. That might just be easier than creating a new one and stuff like that. So you kind of throw it up there. So that, in terms of homework, is the last one that you do need to still turn in, which was 19, because I think we kind of postponed it because we only did part of the chapter, I think, on the exam. Other questions on any of that stuff? Okay, again, if you do have any questions, you could feel free to email me. And other than that, again, good luck on our finals. Good luck on the rest of the finals that you have. Remember, you do need to kind of take these things during the scheduled time so you don't conflict perhaps with any other classes that you may have. So again, the finals will be given during our scheduled period. Okay. If you do have a question or anything like that on lab, what I'm going to do, again, just so it's a little easier, so I don't have to edit so much, I'm going to stop this recording and give me about 3 or 5 minutes, and then I will open this back up. And if you do have questions, you can come back in. I'll hang out for a little bit and answer your questions. Okay. But I'm just going to stop this one for now so that, like I said, I don't have to go back and kind of edit it or anything like that. So, give me about 5 minutes after I stop this, and I'll reopen it if you do have questions. If you don't have questions or anything like that, reminder, I think you still do have that one lab out there. Make sure that gets turned in. And again, if you have questions over the weekend or anything coming up, make sure you feel free to email me. And like I said, I think either today or sometime tomorrow, there may be another kind of take home type quiz. It might be a review type quiz, which will hopefully help you as well going into the final. All right. I'll see you if you do have a question in about 5 minutes. If you don't, have a very good weekend, a good week, and I guess a good summer as well. Yes.